Thanks a lot for the introduction. I'm going to present joint work with Frédéric Magniez and LM Kachefi about non-destructive zero-knowledge proof on quantum state and multiparty generation of authorized hidden GZ state. So in this talk, I will present two orthogonal results, basically. On one hand, so we'll start from what we call classical client remote state preparation. So in that kind of protocol, we can basically prepare some qubits by doing a huge superposition. So it's a step which is quite expensive to do. And the problem that giving just one big superposition, you can only produce one qubit. So we'll try to be more efficient and produce more qubits. So we'll try to generate what we call GZ states. And using a single superposition, we'll try to create many output qubits that will be usable later on. And then we'll see how we can so create this kind of state, but in a multi-party setting. So this is one result that we'll show first. And independently, we can also do zero-knowledge proof on quantum state. So I will explain that a bit later. And at the end, when we combine these two results, we'll get what we call authorized multi-party GZ preparation. But let's start from scratch. So I guess you all know that you can describe some qubits using this K0 notation. So a qubit can be up, down, or in any state. But at the end, when you're a user using some kind of qubit, you will just receive a qubit, and you have no way to describe that qubit. Your only option to learn information about that qubit is to measure it. And when you measure that qubit, you will destroy your qubit and learn one bit of information in that case. So the problem that when you do so, you cannot learn any information about that qubit except the one bit of information you will learn. And for instance, you cannot, for example, check properties on that qubit without destroying it. For instance, maybe you would like to check when you receive a qubit whether it's in the 0-1 basis or plus-minus basis. And with the current tool we have no way to do that kind of check directly. And now we can also start to look at more interesting states. So now we can combine two states, so we can get a K00, and now we can do superposition on that in order to create, for example, this Bell state, which is 00 plus 11. So I will represent Bell states and more generally entangled qubits with that kind of notation. And the state that we will try to look at is the following. So I will call them hidden GZ state. So why hidden? So basically you have some sort of GZ state. So a GZ is like a Bell state except that you have more qubits. And then you will hide this state in between some normal qubits which are not entangled with your main state. So here it's just some K0 state. And then in order to do some hiding, we will hide some local Z operation and X operation in order to hide the state that you have. And by the way, if you have any question, feel free to ask in between. So basically, here I just represented a quite simple hidden GZ state. So you have a GZ state which is made of two qubits. So these two qubits are entangled. You also have another qubit which is not entangled. So this one may be a K0 or a K1. And on top of that, we may apply some local X to rename locally the 0 into a 1 on this one, that one, or that one, and a Z operation that will basically bring you minus there. And I will call the support of this GZ state basically all the qubits that are entangled together. So here are these two qubits. And then, of course, so if you just look at this state directly, then it will not be, so your support will not be hidden because it's always the first two qubits that are part of the GZ state. So then in order to hide this support, you will basically scramble, like do a permutation of all your qubits, and that will be our final generalized hidden GZ state. So it is a permutation of a GZ. So why are GZ states useful? So first, there are generalization of Bell pairs. So it means that you can do some sort of teleportation in order to teleport a state to an unknown party. And we'll see maybe some application to quantum onion routing if you want to send a qubit to an unknown party using an untrusted network. Then DGZ states are maximally entangled quantum state. It has many useful properties. For instance, they can be used in quantum state sharing. So if you want to share a qubit among many parties, you can use it to do anonymous transmission and so on. And so basically, our goal will be to prepare that kind of hidden DGZ state in between multiple parties. And so it means that we will be able to run any protocol that uses DGZ or Bell pair among an unknown subset of parties. So first, I mentioned before the remote state preparation protocol. So I will introduce you quickly what the goal. So usually if you have two parties, so Alice and Bob, if Alice would like to send some qubits to Bob, if you have a quantum channel, it's easy. You can just take the qubit from Alice and send the qubit to Bob. Now, the question becomes harder if you have only classical communication between Alice and Bob. So in that setting, multiple protocols have been defined in order to do what we call classical client remote state preparation, in order to make sure that at the end of the classical protocol between Alice and Bob, Bob will end up with a quantum state, which will be unknown to Bob, and in such a way that Alice knows the classical description of that state. Yes. So in this, so from now on, we'll try to achieve the following protocols. We'll have many different parties. So all the clients will be called applicants here. So you have many applicants that would like at the end to share some DGZ state together. And some of these parties are authorized. So they have some password maybe, or maybe some organization gave them some secret private keys. And so all these applicants will be said to be supported, because at the end they will be in the support of the DGZ state. So in the, they will have a qubit which is part of the DGZ. And so at the end of the protocol, the client will basically talk with Bob, the server, and they want to make sure that nobody knows who is part of the support or not. So this, the identity of all the parties that knows this secret here, which are represented with some green keys in this drawing. So the set of this player will be hidden to any other player. Moreover, so if the server is honest, so only the people that knows the secret, maybe the secret signature of password from the authority, can be part of the final DGZ state. So it means that if, for example, this user would like to be part of the DGZ state, then he will not be able to do so. And also, we want to make sure that if you're a malicious applicant, so let's say, for example, that this applicant would like to tamper the state that will be shared at the end between all the parties, then we want to make sure that this malicious applicant cannot alter the state obtained by other parties. So this will be true. So in that setting, we assume the server to be honest for that specific property, but the property of blindness, which is the one that that makes sure that all the applicants will never learn the DGZ status of other applicants. So this one holds even if the server is fully malicious. Okay, so before I mentioned a few protocols to do remote state preparation. And we could say, okay, maybe we can just directly use these protocols, but so there are different problems. So the first one is that in the protocol, you need to do a very expensive operation, which is a superposition. And at the end of the protocol, from one big superposition, you can just output a single qubit. So it is quite costly, because if you want to prepare n qubit, you need to run at least n times the protocol. Then it's also single party, so you just have a client and a server, and it does not apply when you have multiple clients. And it will not provide any guarantee to the server. So if the server is honest, then at the end of the protocol, the server will have no guarantees on the state that he will prepare. Now there are different protocols that there is some protocol that could be used. For example, the one that can perform generic quantum multiparty computations. But the problem that first the client needs to have very large quantum capabilities in order to do this protocol. And in our scheme, we prefer to have a more centralized approach where you have a weekly quantum client and a strong quantum server. And most importantly, in our setting, in this generic quantum multi-party computation protocol, you have many rounds of communications. And in our case, we would like to have a non-interactive protocol with at most one round of communication. Okay, so now let's try to see how we can first create this GZ state from multiple clients. So we need some kind of assumptions, cryptographic assumptions. So we'll assume so far that we have a family of functions. So they are described with this fk. So k is a public key, an index of the function. And you have a way to sample, so a public key together with a trapdoor using this gen function. So now this family of function fk needs to have some properties. So first it needs to be 2 regular or 2 to 1. So it means that for any y in the image, you have exactly 2 preimages that will map to the same y. Now it also needs to be one way. So it means that this function is hard to invert. If you know the y, you should not be able to find x and x prime. So this is true only if you know only the index k. Now remember before from the generation algorithm, you also obtain some trapdoor tk. And given the trapdoor, even so if you know the trapdoor, then you should be able to invert the function easily. So given the y, you should be able to get both x and x prime. And finally, so this part is a bit new compared, so this part is a new part. So we also want a hardcore bits property. So basically, given the index k, it must be hard to find this string d0. So d0 is part of the generation, is an input to the generation algorithm. And so given the k, it must be hard to find this d0. And what property do we have on this d0? We'll need to have always the, so for some function h that are also part of the protocol, you always must have h of x XOR h of x prime, so where x and x prime are your 2 preimages. So this quantity must always be a constant equal to this d0. So these are the properties that we would like to have in order to have the security of our protocol. And I will explain later, but we have some candidates that are based on the Mitchen-Schwann-Peckert construction. Now we'll see how the protocol works. So we have Alice and Bob as before. So Alice will first sample our trapdoor and the public index for some string d0. So I forgot to mention, but this d0 will be actually the support of the GZ state. So it means that when, so d0 is a bit string, and if at the position I, you have d0 I, which is equal to 1, then the ith qubit will be part of the GZ state of the support. So then Alice will send the public key of this function to Bob. Bob will compute this circuit. So first he will just take some, so this register will be the input of the computation, and the next 2 registers will be the output of your unitary. So first you will just create, for example, using some Adamor's gate, a uniform superposition on all the inputs of our function. Then we'll apply in superposition this function here. So it will basically compute f, k, and h of x on the 2 registers. And then, because this function is 2 to 1, we can rewrite that expression here as follows. So because we have the, so we can sum on all the possible outputs, and for every y, we have 2 preimages, x and x prime, so we can factor out the y and rewrite it that way. And now the server will now measure these last registers, will collapse this huge superposition into a much simpler state. So you will have a y outputted by the server, and on the first 2 registers, you will have the superposition of x and h of x together with x prime and h of x prime. So at that step, we already have something interesting, which is that the server Bob does not know the trapdoor, TK, so we cannot compute x and x prime. So at that step, the server has a state that he cannot describe. On the other side, Alice knows the description of that state, so she can just use the trapdoor, invert the y, and she will be able to learn x and x prime. And so at that step, we have a state that Alice can describe, but Bob cannot describe. But remember, we like to have some hidden digit states, so we need to continue to work on that state a bit more. So first, we want to get rid of that part of the first register, so we'll just measure that register in the Hadamard basis. So what this will do is that so we will get some measurement outcome BIs, and on the last register, you will have basically the same state as before, h of x and h of x prime, together with a random phases. So this -1 to the a will just come from this measurement here. So I will give you the exact shape of alpha here, but what is important here is that we have h of x plus some phases times h of x prime. So now, if you look at that state, you will realize that in fact it is an hidden digit state. So why? So let's say, for example, that you have a bit in h of x which is okay. So here you can see that it is a kind of digit state, because if you have two qubits, so if the first bit, for example, of h of x is equal to the first bit of h of x prime, then it will just be a normal qubit that you can factor out of this state. And if they are equal, in fact, it will be part of the support. So now it's time to give back the result to Alice to make sure that Alice can describe that digit state. So we'll send back the outcome of all the measurements. So here the y and the b's. And as I said before, you can just invert your function, obtain the two preimages x and x prime, and compute the alpha, so these phases that you have in front of the second term, using this simple computation. Now remember, before we said h of x XOR h of x prime must be a constant, which is equal to this string d0 that Alice picks before. So because we have that property, so basically we say that if at some bits I, h of x is different from h of x prime, then these bits, these qubits will be part of the support of the digit state. So here, because they are different only when d0 is equal to 1, then d0 will be actually a description of the support of your digit state. And then you have some correction, the z alpha and x to the h of x prime, that are useful if you want to come back to a canonical digit state, meaning a state with ket zeros plus ket ones. Okay, so now that we saw the protocol to come up with a digit state, let's see how we can construct the family of functions that we need. So first, the first step in our construction is to use the Minchencho and Peckert construction. So in this paper, they give you a way to sample matrix A that looks random. So this is a matrix in ZQ, and it has m rows and n columns. And so if you compute AS plus E, then the final vector, so S and E are some vector that needs to be properly chosen. So E needs to be small. Then the final vector, AS plus E, must be indistinguishable from a uniform vector. Moreover, what is interesting is that this Minchencho and Peckert paper also provides a trapdoor R. So when you sample this matrix A, in fact, you first sample a trapdoor, and then you obtain your matrix A. And given this trapdoor, you can invert. So given AS plus E, so one vector, you can come back to S and E. So you can also represent that property graphically here. So this problem is known as the learning without problem, because basically your goal is to learn the value of S when you add some noise here, the E. And so when you look at all the possible values of AS, you will end up, in fact, with a lattice. So all the black points here can be obtainable by taking some element S, computing in S, A of S, and then just plotting that point. So you will have a lattice, and then when you will move your point with this noise here, you will end up with a point. So for example, here this T, which is close to a point of the lattice, but not exactly on this lattice. So you can see here that, so the problem is that basically you're given these points here, so the red points, and your goal is to find the error here and the S, so basically the coordinate of this lattice point. Okay, so this is difficult to do, and it will be why, so it will be used in the security proof of the protocol. Now, you also want your function to be delta to, so 2-to-1 function, so you want to have two preimages. So the idea is to first sample a fixed vector, so here it will be this y0, which is as0 plus e0. So we'll first sample a fixed vector, and which will be part of the description of our function. And then to compute any other vector, you will just compute, so for any S and E, what you will do is that first you will compute AS plus E, so it will give you 1 point. And to add the other preimage, you will also compute AS plus E and add this fixed vector here. So basically we define our function f as follows. So you have one more bit C that tells you if you're basically sampling, computing the first preimage or the second preimage. And you will compute AS plus E, and when C is equal to 1, you will add this vector y0. So now you can see that you always have, so most of the time, let's say, you have two preimages, because you have the preimage that appears when you don't add the y0, and you have another preimage that is distant by this fixed vector y0, which gives you another preimage. Okay, so now you have some subtleties, because so when you are close to the center, you do not have many troubles, but the problem that when you are out of, so when your error is too big, then you cannot invert anymore your function efficiently. So we have some care, so some cares must be taken in order to make sure that your vector, to make sure that your function is actually 2-to-1 with a good probability. So basically we want to sample our fixed vector with a very small noise at that step. And we can make sure that these kind of functions are 2-to-1 with overwhelming probability as soon as we rely on LWE with super polynomial noise ratio. Never mind. So now we have a way to have a delta 2-to-1 function. And the next goal now is to make sure that we can encode this string D0 inside our function. So usually there is the paper Regev, made by Regev, which basically tries to encode some qubit by adding a noise. So basically if you want to encode 0, you do not add any noise. And when you want to encode a 1, say, you will add the highest noise that you can imagine in this modulo ring, which is Q over 2. So now we will do the same, but instead of just adding sometimes Q over 2 when you want to encode a 1 and sometimes 0 when you want to encode a 0, we'll do the same but for a whole vector. So here, in order to encode the 0, we'll add Q over 2 times our string D0. So the D0 here will be the string that we want to encode. So this will be again added to the fixed vector y0 that we computed before, and we need to update our definition, our function definition accordingly. So now we have S and E, which are as before the lattice point and the noise. Then we have the C, which tells you whether or not we'll add this y0, and you will have this D, which will also add this same vector here. So the hope is that by adding that vector here, we will cancel the part of the y0 that was added before. So more specifically, so what we can see that you have basically two preimages again, as before, one when C is equal to 0 and one when C is equal to 1. And if you do the math, basically you can, so if you have basically f of SE0D, which is equal to f of S prime E prime 1 something, then you can factor everything. So you can bring the S together, you can bring the error together, you can bring this part together. And because you're working modulo, so because the sum is over Q over 2, then in fact you will, so this vector will be equal to this vector only if you have S which is equal, so this vector which is equal to, sorry, so in the second preimage is, you will have S minus S0, E minus E0, 1, and D XOR D0. So basically we have two preimages always, most of the time, and you can check that you have always the XOR of this last element, which is always a constant, D0. So here we have a way to find our hash, our function h, and it is quite simple. So h of x will simply be the last part of your function input. And why is it secure? So remember, we wanted to make sure that given the image, you cannot recover D0. So the proof is not super hard. It's just to realize that AS plus E is supposed to be a uniform vector. So it's supposed to be indistinguishable, from a uniform vector. And so if you add some constant vector, so here, it's there. So if you add this constant vector to a uniform vector, then it's impossible to distinguish whether or not you added that vector. So it's impossible to come back to D0 from that state. Okay, and now we are good. So we have a family of functions. There are approximately 2 to 1. So here the public key will be that one, A0 plus E0 plus this quantity. Then we can define our function as explained before, and the security reduces to the hardness of learning with error. If we are happy to use SWE with super polynomial noise ratio, saying that you are allowed to have a very, very small noise, then we can make sure that our function is 2 to 1 with overwhelming probability. Okay, so now we see how we can construct one state, which is a DZ state. So from one superposition, we can create n qubits, which are part of a DZ state. Now we would like to add what we call zero knowledge proof on quantum state. So we like to make sure that the server, we like to make sure that the server can check some properties on the state that it just got. So first, let me introduce you some what is classical zero knowledge. So we will say that a protocol is a zero knowledge proof or argument when you have a prover and a verifier, and you want to check for some relation between inputs and witnesses. So the prover would like to check that the verifier knows a witness W, which is in relation with a public input X. And so this is a proof of knowledge, so it means that the prover can really prove to the verifier that they know some witnesses, but it must also be zero knowledge in the sense that it does not reveal any information at all about the witness that you use. So basically, your classical zero knowledge proof, if you can prove that you know the secret, but without revealing the secret. So, for instance, the prover can we can prove that there exists some integer p and q such that given n is equal to p times q. So it could be useful, for example, to prove that we know the secret of RSA public key, for instance. And we can make sure that we never relieve neither p nor q. And in our case, we will do more or less the same, except that we will be willing to prove that the function fk is indeed honestly generated. So it must be 2 to 1 with overwhelming probability, and you must have this property with the D0 and so on. And you can do that basically by just proving that your trapdoor has a small enough singular value. So basically we can prove that the function fk is honestly prepared. And basically, so classically we can prove that that kind of properties for any relation which is in NP. So it's quite strong. So in particular, this problem here is easy to check. So there exists a zero knowledge argument for that. Okay, and now what is a protocol with zero knowledge? So it's basically the same as before, except that Alice will also add the proof that the K was honestly prepared. So now Bob can check the proof. He can compute the circuit as before, and as soon as the proof is correct, he knows that K is indeed correctly prepared, and that at the end he will produce some sort of digital state. Okay, so now basically this trick is quite simple, but we managed to have a non-destructive zero-knowledge proof on quantum state. So at that step, the server can check some properties on the quantum state. So here, he can check that it is indeed a digital state, but he will never destruct the state that he obtained. And intuitively, why it is that? So it is just because the server can check if the classical instruction that was used to prepare that state were honestly prepared or not. Okay, so now let's see how we can do how we can extend that properties to multi-party digital preparation. So now the idea is to add a few more requirements on the function that we want to compute. So here, basically, you have the same properties as before, except that you want to be able to locally compute the function. So now we have n parties, or here it would be n generation function. And when you, so each party can generate locally some trapdoors and some public key. Using this trapdoor and this public key, you can compute as before the index k, which is just the concatenation of all the local public keys. And using your local trapdoor, you can locally invert the function. So you will run some x, so part of the input x, and you will have the property that if every local party will locally invert the function, then at the end, f of the concatenation of all inputs will be equal to this y. And the construction is not too crazy. So basically, the first assumption is the same as before, and now we'll just sample many times the same function and concatenate the output of this different function for when you fix the value c, the bit c. Okay, so now we can check what is the final multi-party computation. So, oops. So now all our applicants will basically sample a key, KN, so a local trapdoor that they will keep for themselves and the public description of the key. Then they will send the key to Bob. Bob will locally compute so the circuit that I showed before. He will end up with this hidden digital state. So at that step, he has no idea where are the qubits, which qubit is part of the digital state and which qubit is not, because this is contained in this D0, which is secret. And then Bob will send all the qubits back to the different applicants. And now each applicant can locally use their trapdoor, invert their function to run the local x, so the x, and then they will be able to correct basically so remember before I said that you have some x correction to apply and some z correction that you need to apply, and so each client needs to use like their input in order to do the correction. So you just have one issue, which is that this Z phases is global. So you have one bit which describes the phases, and this bit must be basically the XOR of any single Z correction. So every applicant will be able to correct a local Z correction, and to know what is the global Z correction that you want to apply, you need to compute the XOR between all of them. So because this may leak some information, what you will do is that you will apply a round of classical multi-party computation in order just to find this Z correction to apply. Okay, so at that step, we know how to generate a digital state with many different applicants. We can now easily extend the protocol by adding a check. So we would like to make sure that all the applicants that know some secret can be part of the protocol this time in order to achieve the initial protocol that we wanted to do. And to do that, every every client will send together with the public key at the first step of the protocol. So instead of just sending this key here, they will also send the proof that either they do not know any secret. So in that case, it means that they so either D0 is equal to 0 and they don't know any secret, so it means that they will not be part of the GZ state, or they can also prove that they know some secret and the D0 is equal to 1. So it means that if they are part of the GZ state, then they know the support. So then it will be the role of the server Bob to check that all these proofs are indeed correctly prepared. And at that step, Bob will be able to check to be sure that indeed the GZ state is the correct one. And he will run as before the protocol, produce the quantum state, and send them back to the client. And the rest of the protocol is exactly as before. So now we have some guarantees on this protocol. So first, the malicious applicant cannot be part of the support of the GZ state without having a signature or a password, because Bob will check, so the server will check that the proof are correct. Malicious applicant cannot alter the state, because the only person that is actually playing with the quantum state is server Bob. So you know that if at some point the state you obtain is not a good one, then you need so then Bob actually tamper the state. And even if you have any coalition of malicious client or applicants, then you can make sure that the server, that this adversary can never learn the status of the honest applicant. So now, what application do we have? So, for example, we could imagine to run this kind of protocol in order to share a GZ state. So, for instance, like as before, our server here may have some qubit that he would like to share. So he will run this protocol, and then he will obtain some GZ state, and then he can use the usual protocols to share a quantum state among many different users by starting from the GZ state. And because Bob did the protocol, Bob is sure that all the persons that will be part of this final GZ state are actually authorized, so they know some secrets. But again, Bob will not be able to know who is part of the GZ state or not. And I'm done. Thanks a lot for your attention.